I'm going to discuss class diagrams. Now you can see here there are 57 slides. Okay, so the owner of these slides is Dr. Timothy Lethbridge at the University of Ottawa. Okay, so if you go to this particular link, then you can download these slides. And first of all, I thank Dr. Timothy Lethbridge for granting me the permission to use his slides to create YouTube videos. Okay, so this is the name of my YouTube channel. Okay, my name. Okay, so now in this YouTube channel, I have a playlist. Okay, I have a playlist called UML, and here under this playlist, class diagrams 1, in the video I have uploaded the video, class diagrams 1. In this video I discussed out of these 57 slides, first one to 17th slide. Okay, then class diagrams 2, here I have discussed 18 to slide number 13, and this video, class diagrams part 3. Okay, this particular video, so I am going to discuss 30th slide onwards. Okay, so now let's begin our discussion. Here we discuss about interfaces. Okay, now an interface, it describes a portion of the visible behavior of a set of objects. Okay, so that means if you consider set of objects, interface means it describes a portion of the visible behavior. Okay, so now you already know classes. What is a class? You already know. And an interface also somewhat similar to a class. The difference is in an interface we do not include instance variables. Okay, we do not have instance variables in an interface, and also we do not have implemented methods. Okay, method implementations are not here. Okay, so that is the difference between an interface if you compare it with a class. And now let's look at an example here. If you look at this, person is a class. Okay, person is a class. Class, and now employee is another class. So here this symbol means inheritance, okay, employee class inherits from person class. That means all the attributes and operations in the person class will be available to the employee class. And here also we have machine class, okay, machine class, and here we have ATM class, okay. Here also we use inheritance. That means all the attributes and operations of machine class will be available to the ATM class. And now here we include an interface. So in order to distinguish, we put inside Gilliman's, we put the term interface, and now name of the interface cashier. Okay, this is how we graphically represent an interface. Okay, so here withdraw, and in an interface we only include method signatures. We do not include implemented methods. Okay, so here we just put the signatures, and this one now actually from this particular interface we use the term realize. Okay, here we use the term inherits. Understood? Inherit. Employee class inherits from person class. ATM class inherits from machine class. In this particular situation, employee class realizes cashier interface. ATM class realizes cashier interface. Okay, so we use the term realize for interfaces. And now when you realize, okay, in this way, when you realize all the methods here we included will be available to our class. Okay, and now the simpler notation we use, other than this we can use a simple notation. It is something like this. Now we use a circle, and like this is our interface. This is an alternative notation. Here also in this way we can represent. Now 31 slide, then let's move to the next slide. Okay, so here we have notes and descriptive text in class diagrams. Descriptive text and other diagrams embed your diagram in a larger document. Text can explain aspects of the system using any notation you like, highlight and expand on important features, and give rationale. Okay, so descriptive text, that means later we will discuss, in addition to our diagram, if it is a class diagram, we can include some text. Okay, so later we will discuss such text. And notes means a note is a small block of text embedded in a UML diagram. It acts like a comment in programming language. So now if we have a class, we can put a note. Okay, to this particular class here. Okay, those type of flexibilities are there in UML diagrams. Now let's move to the next slide. Here we discuss about a particular language, OCL, object constraints language, object constraint language. Okay, so actually this is what I meant in the previous slide, descriptive text. Okay, so OCL is a specification language designed to formally specify constraints in software modules. That is a specification language. So once you have drawn the diagram, then we can write constraints using OCL, and OCL expression simply specifies a logical fact, a constraint about the system that must remain true. Okay, once you write a particular statement using OCL, that statement should be true in our system. Okay, a constraint cannot have any side effects. That means once you have applied, once you have written certain constraints, they cannot have any side effects. That means it cannot compute an unboolean result nor modify any data. It cannot modify any data available in your system. Okay, it is just a constraint. OCL statements in class diagrams can specify what the value of the attributes and associations must be. Okay, so values of the attributes and associations, okay, nature of associations, those type of things we can specify using OCL. Now let's see. These are the OCL statements. They can be built from references to role names, association names, attributes, and the results of operations. And logical values, true and false, we can use to develop OCL statements, and also logical operators and or equals, greater than, less than, or not equals, string values as a string, integers and real numbers we can use, and also arithmetic operators we can use. Now let's look at an example, then you will understand. Okay, now this is an example. Here a certain this is what I mentioned as a knot. Okay, now this diagram it has a here linear shape. This class represents sorry, linear shape. This is okay, so from this we can inherit here path. Path is a linear shape. Okay, path means, now linear shapes means path is something like this. Okay, sequence of line segments. Okay, path is something like that. So there is a method to compute the length of the path. Okay. Then again, here we have line means actually a line line segment. No, not a line segment. Okay, line, understood? Infinite line. Okay, then a polygon means something like this. Okay, a polygon. Okay, so now again here linear shape can be formed using line segments. This is our line segment class. Here we have a start point, data type is point, end point, data type is point. Point means, now data type is point means you can specify two coordinates. Coordinates of a particular point you can specify, and there is a way, now there is a method to compare. Yes, here in order to compute the length, here actually it should be something like this. Return type is int. Okay, in order to compute the length, there is a method to compute the length of the line segment. And now this is our class diagram, and also here we have inheritance. Regular polygon, and this is our class diagram. Okay, then here we have an association. Linear shape is associated with line segments, and any linear shape, okay, can have one or more line segments, and that line segment we call an edge. Okay, we call an edge. So this is our class diagram. Now I am talking about how to use OCL and nodes. Okay, this is actually a node, comment like thing. It describes this class. A linear shape is any shape that can be constructed of line segments in contrast with shapes that contain curves. Okay, in that way it describes this particular class. And now let's look at this one. Yes, that means here we have written something using OCL, that means edge, for all, okay, E1, E2, E1, E2. We are talking about edges, edges for all two edges we take for all E1 and E2. Okay, then it is something like this. E1 not equals E2. Two edges are not equal implies two edges are, we say two edges are not equal, that means start point of one particular edge. Okay, start point of one particular edge not equals to, here I write the rest, not equals to start point of the other edge and end point of one particular edge not equals to end point of the other edge. Okay, so this is the expression we write here. Okay, that means we talk about edges, that is why we have put edge arrow, and that means if you consider any two edges, if two edges are not equal, then it implies starting points of the edges are not equal and also ending point of the two edges are not equal. Okay, that is a constraint we have applied, and here that means if you have two edges, they are not equal means starting points are not equal as well as ending points are not equal. Okay, that is simple thing. I just want to explain how OCL can be used. Okay. And now the other thing is here. Now linear shape now associated with line segments. For an example, if it is a path, it is a set of line segments. Okay. If it is a line, okay, it is also composed of line segments, and if it is a polygon, it is something like this. Okay, this is an example polygon, and now the order is important. Here to this edge we have connected this one, then to this one, to this one, to this, likewise 1 2 3 4 5 6 7. Okay, here also order is important. Okay, 1 2 3 4, likewise the order is important. Therefore here we can specify that ordered, that means order is important. Okay, order is important. It is not that legible. Okay, so in this way we can specify that it is ordered. Okay, so that is also a part of OCL. Now you can see OCL we write within curly brackets. Okay, Now another thing, here you can specify, if you consider particular line segment, in order it to be a line segment, what should happen? It's this is the, let's say this is the starting point and this is the start point and this is the end point. Then if it is a line segment, what is the constraint? Start point should be not equal to end point. This is the constraint. Okay, if these two are equal, that means it is no longer line segment, it is just a point. Okay, so in that way we can write a constraint for the line segment. Okay, so again, now if you look at this path, a path means something like this. It is a sequence of line segments. I have told it earlier, and its constraints length of it. Okay, length of it equals edge length okay, and we get the sum. Okay, so this is an array. This is an array. Okay, so here length means edge length. Okay, length of an edge. In order to compute the length of the path, edge lengths, we get the sum. Okay, that can be written in this way. Okay, so then below this one, in order it to be a line, then the constraint is edge size, edge size is 1. That is the constraint. Okay, size is unit 1. Okay, in that way you can write that here. If it is a polygon, polygon means, now you can see it is like a cycle. So for the polygon we can write the constraint. We deal with edges. Okay, then first edge is start point. Start point equals edge. We deal with edges. Last one, last edge. So since I do not have space, I write it here, dot last dot end point. Yes, here I can write end point. Okay, so we end the curly bracket. Now here start. Now let's say 1 2 3 4 5 6 7 8 9 10. Therefore now this is the starting edge. Okay, starting the first point. start point of the first edge should be equal to the end point of the last edge. Okay, so here we start starting point and ending point, start point and end point of the edge 1. Now similarly, now this is the start point and this is the end point of edge 2. Likewise, we have the same convention here. This is the start point of the last edge and this is the end point. This is the end point of the last edge. Now this says the start point of the first edge and start point of the last, no, end point, yes, end point of the last edge should be coincide. Okay, in that way we can write a particular constraint. And now let's see a regular polygon. Regular polygon means if it is a regular polygon, all the length of all the edges are equal. Okay, that is the constraint for regular polygon. Therefore we write the constraint edge for all E1 E2, for all edge, if you consider for all E1 and E2 edges, E1 length equals E2 length. Okay, this is the constraint. Okay, in that way we can use OCL, object constraints language, to apply constraints, and we can use nodes. Okay, we can use nodes like this. Okay, this in order to describe certain parts or entities in our diagram. Okay, so let's move to the next slide. Now here we discuss an example. A class diagram for genealogy, and here let's say this is just an example. Let's look at this example. Okay, if you have the person class, okay, we have an attribute name. Okay, then sex is an attribute, place of birth, that is an attribute, date of birth, that is also an attribute, place of death, date of death, okay, place of marriage, date of marriage, and then finally date of divorce. Those are the attributes 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. Okay, so this is a particular class. This is just an example. We are going to investigate its weaknesses, and now let's say we put a, what is this? A reflexive association, and here two persons. If you consider two persons, now the role here is husband, and here 0 or 1. Okay, and here role is wife, and multiplicity is 0 or 1. Okay, the meaning is if you consider one particular person, that person can have no husband or at most one husband. Okay, so if the person is a female, then she has a husband. Okay, if the person is a male, he does not have a husband. Okay, if you look at this from the other way around, if the person is a male, then he does not have a wife. He has a wife. If the person is a female, she does not have a wife. Okay, that is why here we have used multiplicity 0 or 1 at both ends, and here we can specify using object constraints language. Here we specify husband, sex of husband is male. Okay, male, that is the constraint in our system. And here here we can put the constraint wife, sex of wife is equal to female. Okay, that is the constraint here. Now again we can have a reflexive association. Here the role is child. Okay, role is child, and here the role is parent. Okay, so now we put multiplicity 2 here, and here 0 or more. That means if you consider one particular person, he or she can have 0 or more children. Okay, that is why here we have 0 or more. If you consider one particular person, he or she can have exactly 2 parents. That is why here we have 2, mother and father. Okay, so here also we can put a constraint. Here we have to write it in OCL. Since I do not have space, I write it here. Okay, actually I should have written it here. Okay, anyway, now with the parent, okay, with the parent, then for all parent, we work with parent. That means now here for all P1 comma P2, for all, for any two parents P1 and P2. That is why, that is the meaning of this one. And here if two parents are not equal, if two parents are not equal, that implies the sex of one parent is also not equal to sex of the other parent. Okay, so this is how we can put a constraint using OCL. Okay, now what are the problems in this diagram? There are two problems. Now what are the weaknesses of this particular diagram? Okay, a person must have two parents always. Here, since here we have two, if you consider one particular person, definitely he must have two parents. Okay, sometimes there are situations one parent is unknown. Okay, in that situations, such kind of situations we cannot model using this particular diagram. Marriages not properly accounted for, and in this diagram we can see marriages are not properly accounted. Okay, so here husband, then and wife, and also there is a problem. Okay, so we think we have to think about a better way of doing this. Then let's move to the next slide in order to understand. Now if you look at these two diagrams, okay, not this is actually the same diagram. Oh no, this is another, these are another two diagrams. Okay, these are another two diagrams. Here we have represented, now this is our person class, and this is our we create another class called union. Okay, so now let's see. Here now we have person class. Okay, we have person class, and here you have union class. Okay, and then there is an association between a person and union classes. One person can have 0 or more unions. Okay, one union has 0 or 1 or 2 or persons, and the role of the person there is partner. Okay, role of the person there is partner. That means for one particular union there can be no people, no persons, one person or two persons. Okay, that is possible. In this way we model. And now here again 0 or 1 parents, here child 0 or more. Now the meaning of this one is one particular union, if you consider one particular union, okay, their attributes are place of marriage, date of marriage, and date of divorce. Okay, so here when two people get married, they might get children and then they divorce. Okay, so in that situation, from one particular union we can get 0 or more children. Okay, in that way marriages are properly managed. Okay, using this diagram than in the previous diagram, in the previous slide. Okay, so now for any child, if you look at any child, for he or she, there can have 0 or 1 parent. Okay, from this particular union, if the one of the parent might have died. Okay, okay, so that is that kind of situations are there. Therefore this is a better way than previous situation. And now here object constraints language we have used. If you consider partner and if you consider two partners, not equals means their sexes are not equal. Okay, that's a simple thing. Okay, that is one particular diagram, and this one is another one, and that is also a better diagram. And now let's see. Person class is here. Okay, person class is here. Now we specialize that person class as woman and man in order to properly account the sexes. So here we inherit from the person class, and now we have a union of now here I will union class. Now here you can see, if we write an association, woman can have 0 or more, one particular woman can have 0 or more unions. Okay, she get married and then divorce, then get married and divorce. Okay, likewise she can involve in 0 or more unions. Okay, then here one union involves 0 or 1 women. Okay, no women, no, exactly 1 women. Here we do not care about the marriages of same sexes. Okay, that is not considered here. Okay, if you consider that one as well, then this diagram is also not sufficient. Okay, here we only consider straight marriages. That means marriage is always happening between a female and a male. Okay, that is the only thing we modeled here. Okay, if you think beyond that, marriage of same sexes and like that, then things become more complicated. Okay, therefore one particular union, 0 or 1 women is involved. Okay, so here the role of the woman is female partner. Okay, then here also with the man we have an association. One man can involve in 0 or more unions. He can marry, then get divorced, again marry, and likewise. And also he can and in one particular marriage he may have children. Okay, then he get divorced and he get married, again he has children, then again divorce, and likewise that is possible. That is possible. Therefore, now here 0 or 1, that means one union involves one man or no men. Okay, no, one man or no men. Okay, so and here the role is male partner. The role is male partner, and now again in one particular union, one woman and man get married, then they, in that particular union, they raise children, they get children. Okay, so the role is a child, they can get from one particular union, they can get 0 or more children. Okay, one child can have 0 or 1 unions. Okay, and the role of them are parents. Okay, so in that way we can model. Now if you look at these two diagrams, now marriages are properly handled in this diagrams. That's what in this previous diagram actually marriages are not properly handled. Okay, so we do not know now which marriage. We here also we have information about children, but from which marriage they have got children, that this child from which marriage. Okay, something, so handling it is difficult using this particular diagram. That is why we first think about this kind of a diagram, then we further think, we revise it into the diagrams likewise. That is how you have to do this modeling with classes. Okay, so it is not a simple task, it becomes very complicated when we try to model huge information systems. Okay, and now this is the last slide I discuss in this particular video. Okay, so now I am talking about my YouTube channel. This is the name of the channel. Okay, in this channel I have a playlist called UML. Then in the video, in this playlist, class diagrams 1, I have discussed slides 1 to 17. Then in the video class diagrams 2, I have discussed 18 slide to 30. Okay, then this particular video class diagrams 3, I discussed from 31 to 37. Okay, then in next video class diagrams part 4, I discuss from 38 slide onwards. Okay, so if you could understand this video properly, if you could get something, if you could learn something, so I have a small request. Please subscribe my YouTube channel, and if you have any questions, then you can write those questions in the comment section below. Okay, then definitely I will answer if you put any question. Okay, and also I thank Dr. Timothy Lethbridge Okay, actually these slides belong to him. He has granted me the permission to create YouTube videos using these slides. And also I thank you for watching the video.